Thanks for joining our Phoenix LiDAR Systems February 2021 webinar. Today's panelist is Corey Kellum, who is a senior post-processing engineer here at Phoenix LiDAR Systems. Corey, the floor is yours.
All right, thank you, Lito. Yeah, welcome everyone. There we go. All right, so if you are unfamiliar with Phoenix LiDAR Systems, we're a systems integrator specializing in compact survey-grade mapping solutions that can be mounted on virtually any moving vehicle, from UAVs to planes, helicopters, backpacks, boats, really you name it. Since 2013, we have been developing complete 3D mapping solutions, enabling customers around the globe to collect and process survey-grade geospatial data from unmanned and manned vehicles. Phoenix is the original pioneer of UAV-based LiDAR systems and has grown to develop user-friendly flight planning, acquisition, and automated post-processing software, which has turned LiDAR into just another common tool in a surveyor's toolbox. All right, so today's webinar, I will be presenting on vehicle flexible systems and what that means and why that is useful and beneficial to our customers. As you can see here, these are just a few examples of the vehicles that our payloads can be mounted on. And so today I will give a high-level overview of just what vehicle flexibility is, why you would want a vehicle flexible system, how we make this physically possible, transferring a payload from one vehicle to another, and then I'll dive a little bit deeper into the technical challenges that we face in doing this task. And then I'll get to the main takeaway of just how we make it easy for our customers, for you guys. So we'll start with an overview. So what is flexibility? Flexibility is the quality of being easily adapted or of offering many different options. And that is exactly what our solutions, our payloads do. They can be adapted to many different vehicles, and they offer a variety of options in the form of applications that are possible. So as I mentioned before, I would say our most common vehicles that we mount to are UAVs, cars, backpacks, and helicopters. And these are some of the common verticals or applications that our solutions work well for. The construction industry, the mining industry, forestry, utility power lines. But the list really goes on and on. And all of our scanners can achieve one of these tasks, or all LiDAR scanners in general can achieve one of these tasks. But what separates us and what makes Phoenix LiDAR Systems so special is that we enable you to achieve multiple tasks through vehicle flexibility. So with the same system, you can capture topography, inspect utility installations, monitor construction sites, map natural disasters. And so a really big question is, why do this? Why is it beneficial to move a solution from one vehicle to another? And the answer is that different vehicles offer different distinct benefits. Whereas in the past, companies would need to use a separate personalized system for each application. Now we make it possible so that you can take the same sensor, same payload, and mount it on different vehicles. Yeah, like in the past, a company would have a car-mounted system. They'd have to buy a different LiDAR system for, say, helicopter operations or something. And so one of the differences in vehicles, or the benefits from going from one vehicle to another, is the vantage point. The vantage point of a scan from the ground is very different than the vantage point from an aerial vehicle. And these LiDAR sensors collect data from line of sight, right? So it depends on the line of sight to the feature. And your line of sight from an aerial vehicle to the ground is very different from the ground to to a feature. So for example, in this image here, it's a screenshot of a ground scan. And we can see really high density, high resolution LiDAR points on poles, on vertical poles. And that's because we can side scan. But if we were scanning this from the air, the surface area from the top down of the pole is very small. So we probably wouldn't get very much of the pole. So that kind of just gives you an example of the line of sight to the feature. So also different projects they have different project requirements. And it comes down to what kind of data density are you looking for? The data density from a car, for example, is much more dense than from an aerial vehicle. What does your site accessibility look like? Can you drive to the site, or do you have to fly to the site? Are there roads? Data coverage is another thing. You get a much wider swath, let's say, from an aerial vehicle than a ground vehicle, or you can potentially get it if there are buildings on either side, or obstructions. And then when it comes to vehicles, how fast can you mobilize that vehicle, and what is the cost of mobilization? So I'll get into some of the advantages per vehicle, and I'll start with the UAV. And this is not an exhaustive list by any means, but just some examples. So a UAV is great for site accessibility. You can essentially fly a UAV to any site. It is an inexpensive and easy vehicle to mobilize. Just throw it in your car, drive close to the site, and then fly the UAV a little bit further to your site, for example, or carry it onto site and then fly it. And you can do nadir scanning with it, which is that top-down bird's eye view scan which is great for vegetation penetration. And from a UAV, you're flying relatively low, under 400 feet, so you get very dense data. If we take a look at the car, a car is extremely dense data, the most dense. And since you are doing short ranging to targets, you'll have extremely high accuracy as well. And since you are side scanning, this is ideal for building wall detailing, capturing those wall features or poles, like I was mentioning before. And when you're in a car, you know how much gas do you have in the tank? You can drive for hours, and you can collect very large areas of interest and along long corridors. And a car is one of the most ubiquitous vehicles out there, so it's an easy vehicle to mobilize. They're everywhere, and they can be really inexpensive. As far as a helicopter goes, you can get very long flight time, so much longer than a UAV, for example. And since you can fly much higher than 400 feet AGL, above ground level, you can get wide area coverage. And when it comes to site accessibility, not only can you fly to the site, but you can pretty much fly legally virtually anywhere in the US, some exceptions, but essentially anywhere. And you get that nadir scanning, that top-down bird's eye view for vegetation penetration as well. And now let's look at some limitations for these three common vehicles. From a UAV, your coverage, your data coverage is essentially limited to how many battery packs you have for your UAV. And so if you don't have a charging station and you only brought a couple of packs, then the amount of data you can collect that day is kind of dependent on those batteries of your aircraft. And there are some airspace regulations. You can't fly in certain airspace. You can't get certain permissions, and you have a ceiling that you can fly up to 400 feet, for example. And if you're scanning near buildings in urban environments, you may not capture the entire side of a building. Maybe you'll get part of it, maybe you'll get all of it, but a lot of times, depending on where your UAV is in relation to the building, you probably don't capture the entire side of it. And that's where a car scan comes in, you can capture that entire side of the building. It's great for that, but it has its own limitations. Side scanning from the ground level is its own limitation because you cannot scan the entirety of deep depressions or ditches that are adjacent to a corridor when you're running a single pass. Or if you have, undulations in terrain or in topography next to the road that you're scanning, you'll have data voids and their laser shadows. And it does not capture the top of building roofs. So if you're concerned with scanning building roofs, it might not be the vehicle to use, or it certainly will not be. Moving on to the helicopter, I'd say its biggest limitation is expensive compared to other vehicles. And it can also take time to mobilize. Like, do you own your own helicopter? Do you have to rent it? Do you have to get a crew to use the helicopter, to operate it? And another limitation is when you're scanning from these high altitudes, it generally does not capture the size of buildings at all. Maybe it'll get some if it's a very tall building, but yeah, it depends on your relationship between the aerial vehicle and the building you're scanning. But this is where you can capitalize on different systems. So you could capitalize on the helicopter's abilities to collect rooftops and then combine it with a car's ability to collect the side of a building, and then scan those areas with both vehicles and combine the scan. And we'll talk about that a little bit later. So when it comes to applications per vehicle, these are just some of the applications. But from a UAV, it's a great application is dense jungle canopy penetration. So you can fly really low and slow and penetrate that dense canopy and collect the micro topography digital terrain model from areas that you can barely even walk because they're so dense. You can monitor coastal erosion or landslides, or do as-built construction mapping and disaster response mapping as well. If you can't, right after a natural disaster, maybe you can't drive the streets, but you can fly it. So that's a great application for UAV, quick to mobilize as well. If we move on to the car, cars are great for topographic corridor mapping. So highways, railways, waterways from boats, for example, and city streets. And you're collecting such dense data that it's fantastic for roadside asset mapping and collecting poles and fire hydrants and that sort of thing, street signs. You can also assess road surface conditions from the high accuracy, high density LiDAR that you're collecting, and assess road geometry. From a helicopter, you can collect very wide areas, as a wide swath, since you can fly high. And this is great for power line and pipeline monitoring, mapping levees or railways and various forms of critical infrastructure that maybe you can't access some critical infrastructure from a UAV, for example, and riparian boundaries. So I touched on it a little bit earlier, but this is an example of how you can use a Ranger LR system in the same day to collect a mobile drive data set and an aerial data set. So if we start with the upper right image, that is data collected from a car scan. It was Ranger LR and a Ladybug used for Ladybug camera for colorizing this point cloud. So the scanner was at about 3 meters above ground level. And the big takeaway for both of these images are the point density and the data coverage or the vantage point. So the point density is anywhere from 900 to 5,000 points per square meter within the mobile drive. That's extremely dense compared to the helicopter, which is still dense, but anywhere from 19 points per square meter per flight line. And if you do kind of cross sections and or excuse me, a grid pattern. If you fly a grid pattern, you can, we were able to obtain 79 points per square meter for this entire data set. And that was flying at 300 meters, pretty high. And notice the data coverage. So from the helicopter, we can very clearly see that we're collecting all of the rooftops, all the building tops. And we are getting some of the ground, but there are definitely some data voids on the sides of buildings. And we don't have the same kind of density and resolution. So this is a great example of, you could fly the city of Los Angeles and then drive the city in the same day if you have time, and combine the data sets to capitalize on the benefits of both vehicles and the vantage points that they allow for. So if we move on to, this is a Scout 32 example. So it's a little bit more cost-effective solution, a little bit cheaper solution. And once again, let's look at the data density and the coverage. The density from a Scout 32 Ladybug drive on top, the image on the top, anywhere from 500 to 1,500 points per square meter, so extremely dense. But this site has a lot of cars, a lot of pedestrians, and we likely wouldn't be able to fly a UAV here legally. So this is a great application where a mobile drive might be your only option, depending on your budget, if you can't fly a helicopter, for example. And Scout 32 isn't necessarily a helicopter solution. And from the UAV data set at the bottom, still very dense data, between 40 and 200 points per square meter, but not quite the density of the drive. However, if you look at those roads in the UAV data set, if we were to drive those roads with this system, we would have a lot of data gaps in some of the areas, the topography that we were looking to capture. So UAV is definitely the right vehicle choice for this terrain. So how can you do this? How can it be possible to use the same LiDAR scanner, the same payload, and move it from one vehicle to another? Well, when we're doing this, there are some considerations that we need to take into account when we're swapping vehicles. The main consideration is the system mount. How do you actually adhere it and attach it, mount it to the vehicle that you're operating? And with that, then there's cable and hardware connections. Do you use the same cabling for a car as for a UAV, for example? Another thing to consider is the reference frames, which I'll get into in more detail later on, of your IMU and your sensors, and also your system calibration. Does that hold up, or do you have to do a whole nother system calibration every time you mount it to a different vehicle? Another consideration is data collection. Can I use the same laptop and software if I'm scanning from a UAV versus a car, for example? So we'll start with mounting options. And as you can see, we have a couple of the common mounts here. So UAV mount uses a quick release system, and same with the backpack. And so those are pretty easy on, easy off. The car mount on the upper left, and then the helicopter on the bottom right, those are more bolt-on, bolt-off solutions. And so like with the car, for example, the vehicle mount, you would take your payload and you'd mount it you'd bolt it onto the mounting plate. And then that mounting plate has thumb screws to mount to the roof rack, which attaches that rigid frame that attaches to the top of your vehicle. And that allows the system to be mounted in the exact same location each time that if you move it from the vehicle to every time you mount it onto the vehicle. For helicopter mounts, there are a couple different kinds of mounts. This is just one. If you're using a smaller aircraft like a Robinson R-44, you will need a heli boom, which we provide. And if you're using a larger aircraft like a A-Star or larger, you'll likely have a nose mount system. They'll have a meeker mount. But either the boom or the meeker mount attaches to our heli mount with vibration isolation, and then the payload bolts onto to this mount. And so in order to provide seamless transition from one vehicle to another, we provide custom cables with different lengths, and they have compatible connectors for any vehicle setup. And so one thing to consider here is that, like, let's take the example of a helicopter setup versus a UAV. A helicopter, the payload is mounted in the front of the helicopter, but the operator is in the back of the helicopter. So you have to have cabling run from the front of the aircraft into the aircraft, and that requires some longer cabling. Whereas for a UAV setup, all the cabling is right there on the drone or the UAV, and it's a lot shorter cables. So we provide you with all you need for whichever vehicle that you're looking for. I touched on this a little bit, but a big part of these rigid mounts is that the main takeaway here is that you avoid the need to recalibrate your system between vehicle swaps. So, and the way we do that is because your IMU to LiDAR relative positioning is fixed. And so you can notice in the top image here, we have the LiDAR mount on the back with the IMU bolted onto it, and it's the same offsets from there to as when we mount that payload onto the UAV. So it does not change from one vehicle to another. So our bore sight calibration holds. And another thing to note is that, from the UAV to the car, our IMU to camera and IMU to GNSS relative positioning, although it changes that distance, it's the relative positioning is fixed for each individual vehicle mount, and that means it's those offsets are consistent and repeatable for that specific mount. So you can move it without having to remeasure lever arms. And I'll talk about lever arms a little bit later on, but essentially it's those offsets. And when it comes to data collection, you can use the same laptop and acquisition software for any system in any vehicle. And that makes it pretty easy. And the Spatial Explorer can handle a variety of different reference frames, which I will get into in the technical challenges, and coordinate systems as well. So it's your one-stop shop. All right, so now I'll dive a little bit deeper into the technical challenges that we face when we swap a solution or a payload from one vehicle to another. The big question is, and the thing we need to know is the position and orientation of our sensors, so our LiDAR and our camera sensors, relative to the vehicle. So do we have our LiDAR facing vehicle backward, like in a car setup? Or do we have our LiDAR sensor facing vehicle forward, like in a helicopter setup? Does that make a difference? The answer is yes. How do we overcome this? The short answer is direct georeferencing. And at this point, let's take a step back and we'll kind of get into what direct georeferencing is and what it does for us. So what is direct georeferencing? It is the direct determination of the position and orientation of the aircraft and sensors. And that's exactly what we want to know. And why is it important? Because it enables us to perform direct calculation of spatial coordinates in output data products like LiDAR point clouds or ortho imagery derived from photos. So if we look at this visual here, direct georeferencing makes this possible so that at any point along our trajectory, we know the position and orientation of each image that was captured. And anytime a laser was enabled, was fired and triggered, we know where that the orientation, where that laser pulse how it was oriented and the initial position that it came from. So how do we achieve this? We have some requirements, and they are fourfold. Number one, we need GNSS-aided inertial navigation. Number two, we need lever arm translations between sensors. Number three, we need to know some rotations, the IMU to sensor and IMU to vehicle reference frame rotation. And finally, we need a bore sight calibration to dial everything in. So we'll start with requirement one. The first thing we need to know is our vehicle's position and orientation over time, AKA the trajectory. And this is determined using a GNSS-aided INS. So you might be asking yourself, what the heck's an INS? It's an inertial navigation system. And so it's a self-contained navigation system comprised of several subsystems. It has an IMU, a navigation computer, a power supply, and an interface, which we use Spatial Explorer. And it uses measured specific forces and rotations to estimate velocity, position, and orientation. You might ask yourself, all right, if we have an INS, why do we need GNSS? And that's where aiding comes into play. And that's a process in which one or more sensors are used to provide data to another sensor. And the result is better data than could be obtained by any one individual sensor. So it improves on the accuracy of your trajectory. All right, requirement number two. Now that we know the vehicle's position and orientation, we need to know the sensor's position and orientation relative to that vehicle. So that's where lever arms come into play. And a lever arm is the relative position between the INS and aiding sensor for the XYZ distance measurements. And so if you look at the bottom here, this visual, we have IMU in the center, and to the right, we have XYZ measurements to the camera sensor. We'd also have a LiDAR sensor, most likely. And then to the left, we have XYZ measurements to the GNSS sensor. So we have two lever arms here. So we'll start with the IMU to sensor lever arm, and this enables the sensor to have a known position relative to the IMU. And then the IMU to GNSS lever arm enables the IMU to have a known position relative to the vehicle position. So it ties everything together. We know where the vehicle is positioned and oriented, and because we have fixed offsets to our IMU and our sensors, we know where our sensors are positioned and oriented in space at all times. All right, requirement three, and this is a very important step. So this important step is an important step in both real-time and post-processing of the trajectory and the LiDAR and imagery data. And that is, we need to define the rotations between, we need to define two rotations. Number one, the IMU local level frame and the vehicle's body frame. And number two, the sensor local level frame and the vehicle's body frame. And so I'll start with the body frame. The body frame is the reference frame of a rigid body, typically the vehicle whose trajectory is of interest. So this body frame is the upper image. You'll see an aircraft there. We have Z up, Y forward, X to the right. And notice how that's different than the IMU below it frame and the sensor frame, the LiDAR sensor frame. So a local level frame is a reference frame in which one of the axes points up or down relative to the local level direction, and the other two axes line a tangent plane. So the bottom line here is that our X, Ys, and Zs, our reference frames, are pointing in different directions for our IMU, our LiDAR, and our vehicle. And to put it very simply, we need to get our X's all in the same direction, our Ys, and our Zs. And how do we do that? We need some rotations. And that is accomplished through a direction cosine matrix, or DCM, which is a 3x3, at least for our application matrix, defining the orientation of one frame relative to another. And this orientation, or attitude as it's called, and hence the direction cosine matrix elements, can then be parameterized by these things called Euler angles. And Euler angles were named after Leonard Euler from the 1700s. And he figured out the heading, pitch, and roll angles used to specify the attitude of the vehicle relative to the local level frame. And we use the Z rotation first, then X, and then Y in that order. And there are, just to dive a little bit deeper, there are two ways to do this. So the three elemental rotations may occur in one of two ways. It can be an extrinsic rotation or an intrinsic rotation. And Spatial Explorer can handle both. And in the past down here, we have an image of Spatial Explorer version 5, for example, and you can calculate these different rotation combinations. So for extrinsic rotations, we have rotations about a static coordinate system. So rotations about the axis of the original coordinate system, which remains motionless. So an example of that is a Phoenix LiDAR systems rotation. And then we have an intrinsic rotation, which are rotations about the axis of the rotating coordinate system, which changes its orientation after each elemental rotation. So basically you would rotate about the Z axis and your whole coordinate reference frame would change, then about the X axis, and that would rotate the whole coordinate system again, and so on. So requirement number 4 is a bore sight calibration. And what is a bore sight calibration? It is the procedure performed to determine and correct for the misalignment angles between the IMU and the sensor frame. So between IMU and your LiDAR and IMU and your camera. So let's give a visual representation here of unbore sighted versus bore sighted LiDAR. So you could have everything right. You could have your lever arm translations dialed. You could have your Euler angles and your rotations correct, and you'll still have your LiDAR looking like that image on the left, where that is an unbore sighted LiDAR system. So there are some there can be some very small tweaks that you can make to these misalignment angles between your IMU and your LiDAR sensor. And then that's what really dials it in and gives you the accuracy that you're looking for in your LiDAR point cloud. And these lines, these points are colored by flight lines, so you can see how many different flight lines have passed over this building. So why do we care? How do we make it easy? So basically, Spatial Explorer version 6 simplifies all these technical challenges for you, makes it easy on the customer. So basically, payload, lever arms, rotations, and bore sight calibrations are now in Spatial Explorer version 6 are all referenced to the IMU frame. And that's a pretty big deal, because in the past, everything was referenced to the vehicle frame, as I mentioned. And so basically, if your LiDAR sensor is mounted vehicle backward versus vehicle forward, you would have to adjust your lever arms, adjust your rotations. And as you can see, it's kind of complex, but not anymore. So now when your hardware does not physically move in relation to the IMU, Spatial Explorer version 6 does not require you to update lever arms and rotations for a system mounted with sensor facing vehicle forward versus vehicle backward. And that is a big deal. All right, so to sum up, the bottom line here is that in the past, a separate personalized system was required for each application. But now, through our innovations in system integration, companies can now easily deploy a LiDAR system mounted onto one vehicle and then seamlessly transition it to another vehicle as an all-in-one 3D mapping solution. And what this does is it maximizes your return on investment by capitalizing on the benefits offered from disparate vehicles using a single scanner. So like we talked about, you could scan, the tops of buildings and the sides of buildings at the same time, or using the same payload or solution. And finally, yeah, we easily and seamlessly transition from one vehicle to another through a couple of things that Phoenix LiDAR system does that we do here. And that's create rigid system mounting, custom cabling, and extremely user-friendly software. So I'm sure you're watching this webinar and you're interested in a LiDAR system. So if you still need help deciding on a system, then please reach out to us and talk to our experts. We're happy to guide you through this decision-making process. There's a lot of IMUs and sensors and mounts out there. And so, we'll step you through what type of environments you're going to be scanning, how large of areas you're going to scan, what kind of accuracy you need. And in learning about your applications and exactly what you need will help you to choose the perfect Phoenix LiDAR solution that fits your needs. So with that, thank you all for your time and for listening and attending this webinar. And I'll pass it back to Lido, and we'll get some of your questions answered.
All right, thank you, Corey. Yes, we do have a few questions that are still open in our question window. The first of these is asking, commenting on the specs for their VUX1LR, which we use for our Ranger LR. It shows a minimum range of 5 meters. Is there a way to customize the range? And because in our example, we showed that we were scanning at about 3 meters. I think, Corey, you have a good answer for that, how we can use that sensor on a mobile platform that's really only about 3 meters off the ground.
Yeah, I would say one thing with the Regal specs is they're pretty conservative, honestly. And we have not seen any issues scanning from 3 meters. We're still getting extremely high accuracy LiDAR from 3 meters. And like that, they also state a max range, and dare I say it, that it can actually go a little bit farther than the max range that they state. But it's just keeping in mind that those are a little bit conservative for those specs.
Also, something to consider is that even though we have the sensor mounted at about 3 meters above the ground on a mobile setup, it's scanning in almost 360 degrees. Typically, at least 180 degrees is what you're looking for the field of view. A lot of times higher. So the targets that are being returned are often much farther than 3 meters or 5 meters. Anytime you go past, even just 20 degrees off of nadir, you're going to be you could easily be hitting the 5 meter, well, maybe not 20 degrees. You could easily be hitting targets well past the 3 meter mark or 5 meter mark as your point of interest if you're going along the side of a road, for example.
Yeah, and that's a great point that Lido brings up. And if it's tilted back at 30 degrees, right, it's, straight down might be 3 meters, but then the hypotenuse of your triangle, for instance, might be at 5 meters. Or if you are concerned and you don't want to keep anything within 5 meters, then you could always use our software to trim everything within 5 meters out. But you're definitely scanning much farther than 5 meters for the majority of your scan. And you could also do multiple passes. So if you didn't want to keep the data right below you, for instance, for whatever reason, you could, and you had a 2-lane road, you could scan it in 1 lane and then come back and drive the other lane, and you would have the coverage of those areas of below 5 meters, for example, if that was a concern to you.
Okay, hopefully that answers your question. And we have another really good question here that we get a lot. What about driving in the car? What's the maximum minimum speeds? Is 70 miles per hour on a highway okay?
That's a good question. There are different speeds for different sensors, so I'll say that. And we do provide software so that you can calculate your point spacing and your line spacing for within your scan. And so you can understand your scan pattern with respect to velocity. So can you drive 70 miles an hour? Absolutely, but it depends on the point density that you're looking for. And maybe that point density is what you're looking for, and maybe it is not. But I would typically recommend keeping, most highways are like 55 miles an hour, and I'd probably recommend keeping it under 55 for me personally.
Now, would tiger striping be an issue if you're driving, if you're doing a mobile scan that fast on a highway, especially with such a short range that you're looking at for your targets?
It also depends on, it depends on your vehicle and the suspension of your vehicle, and there are a lot of factors. The type of road that you're driving on, right? Is it a dirt gravel road? Is it a paved road? It's hard to give a single answer, but since there are so many variables, but generally, we have many customers out there driving at highway speeds and collecting data that suits their needs and that fits their project specs.
Okay. Next question I have is, how does LiDAR work for penetration on vegetation? On dense vegetation, they need to detect ground irregularities. What are the most important parameters to select the better model for these purposes?
To select the better model for your purposes. So,
should they be looking at a single laser or a multi-laser? And what are the important factors in getting a good ground scan from dense vegetation?
Yeah, that's a good question. So, I mean, there are certainly differences in accuracy per scanner, and the single laser scanners tend to be more accurate scanners, more precise. I will say more precise. The accuracy generally stems from your GNSS and IMU sensors being used. So if you want the most precise and accurate LiDAR ground model, I would use a single laser paired with a high quality IMU. But you can certainly get good high accuracy data, not as high accuracy data, with a multi-laser system. And then as far as, there's single laser systems that have a high pulse repetition rate and can pump out a lot of laser pulses per second. And then you have more dense data. Data density is also a concern when you're penetrating vegetation, because you want as many laser pulses shooting through the tree canopy as possible to try to maximize your chance of getting passing that laser pulse through a void within the tree canopy, right? Because if you're just hitting leaves, unfortunately, LiDAR is not a magic sensor. It doesn't go through leaves, and actually has to hit, a void that that laser pulse can see from your sensor all the way to the ground. So you maximize your chances of hitting the ground with a sensor that that pumps out more pulses per second. And that's a great thing about the multi-lasers, is that they give you a lot, generally, depending on the sensor, they give you a lot more pulses per second. And so if you are trying to penetrate tree canopy, you're sending a lot of shots through. Maybe it's not as accurate or as precise as a single laser, but you have a good, you can generally extract a very dense ground model using multi-laser systems.
Okay, thank you, Corey, for that answer. Next question I have here is, do you provide solutions to perform segmentation of the reconstructed scenes? And if so, how customizable is it to accommodate different applications?
Segmentation of the reconstructed. So that would be, do we provide that? We definitely sell software where segmentation is possible, and we provide extensive post-processing training to get you to a point where you can classify and segment your point cloud for your project needs. So short answer is yes, we do. LiDAR segmentation and classification is extremely common. We teach each customer that needs training. We teach them these skills. provide those skills.
Okay, the next question I have is, when will Spatial Explorer 6 be available? The only thing we can say is soon. We don't have a firm answer for that yet, but it is coming soon. So look forward to that, and us doing an announcement on that when it is ready for prime time. Okay, let's see here. Next one I have here is hold on, I'm looking through some interesting questions here. Going back to the VUX1LR, how flyable is the VUX scanner on an M600 Pro, as it is very heavy?
That's a really good question.
It is a good question. Yeah, it's very possible. We've in the past couple of years, we've upgraded our navigation box to our new air nav box, which is very lightweight. I think it shaved about 600 grams, at least 600 grams off of the old nav box. So it's possible it makes it possible to fly any of the VUX models, the HA, oh, not the HA, let's say the LR, the UAV, with an M600 Pro, and still have enough time to do your calibration and get some decent data. So yes, it is possible. Of course, we are now looking at the models, the UAV models that are extended heavy lifts, like the Alta X that we offer, or even the if you're looking at the hybrid models, the Harris H6 H Plus, which is a hybrid fuel, electric and gas UAV, but those can give you long flight times, into the in 45-minute range plus. But it is still possible to use a VUX with an M600 using our AirNav box, our latest model. So absolutely. Okay, let me step back here. Okay, one question here is, are the frames only suitable for Phoenix LiDAR systems, or can they be used with other systems? We do not integrate other companies' LiDAR systems to be used with our roof racks or backpack mounts or anything. They are specific for our company's products. So unfortunately, the answer is no. Okay, another question here. Are there any health concerns when working in a more populated area? That's a pretty general question. Corey, how would you take that one?
Health concerns in working in a more populated area. We talking about COVID health concerns? Or eye safety? If we're talking about eye safety, for example, our lasers are all eye safe, and so as far as eye safety goes, people are safe. You can scan in populated areas and above, from a helicopter if you're flying over, then you can. And if you're driving next to them, then they're also safe. So the answer is yes.
Yes, as far as eye safety goes, we do have one product offering that is not that's a little more powerful than the rest, our VUX 240, where it is where in general use when it's on a helicopter scanning from helicopter range, there would be no issues with eye safety, but when working close range with it, for example in the lab or mounting it, there might be concerns, but in general, the majority of our line, in fact, everything but the VUX 240 does have eye safe lasers. Okay, let's see here. Oh, okay, here's a good question. What RGB colorization capability do your systems have?
Yes, we can do it. We have a lot of different cameras, whether it be from a car, we use the Ladybug camera, and from the air, we have quite a variety of cameras. But the RGB, from any of these cameras, the RGB pixel values can be encoded into the LiDAR. As the presentation showed with the mobile drives and from the aerial drives, you can accurately colorize any point cloud with these cameras. And some of our solutions are actually 4-band as well. So you can get the near infrared, or we also sell thermal cameras, and you can colorize other bands into the imagery of, or excuse me, into the LiDAR as well, and create multi-band orthomosaics. So like, 4-band, 4-band orthos.
Yes, for standard cameras, our current offerings are the A6000, our A6K Lite, which is our own version of the A6000 in a smaller and lightweight package, which makes it even more flyable for use with heavier sensors. We also offer the Sony A7R4 and A7R2 units, as well as a few phase 1 models, the IXM50 and IXM100. All of those we regularly integrate with our LiDAR packages. Okay. I'm not sure if Corey, you might know what this means. Hi, is it possible to fly at 100 KTS, for example? Oh, knots, 100 knots. What's the conversion for knots to miles per second?
That's
meters
really
per second.
fast, but it depends on the sensor. I'd say there's one sensor that can, and the VUX240 could fly at 100 knots. But typically, we fly, if we're doing helicopter operations, 55 to 60 is normal. But yes, you can fly the VUX240 at 100 knots.
Okay, we got a couple more questions here.
That would be the Ranger XL. Sorry.
Oh yes, the Ranger XL. That's right. Which uses the VUX240 sensor. That's our Ranger XL. Here's one: is it possible to incorporate a ground scan with an aerial LiDAR scan? Yeah, we've already discussed that. Where you can combine, and we'll teach you how to combine ground and aerial scans, or scans of different types, even taken at different times, together for one point cloud. So that is possible. If using a pre-V6 Spatial Explorer to process car collected data in a separate project than UAV collected data, okay, this is something that we might need to answer offline. So I'll skip that one for now. Next question, I guess this would be the last one we'll ask. Is there a LiDAR next generation system? What will the new and improved LiDAR be able to do that it can't do now? Unfortunately, we don't have a crystal ball. If we did, we would all be very, very rich. But Corey, are there any features that you see on the horizon that you might want to, that you can talk about, or that you can even speculate?
Like you were saying, it's hard to predict the future, but we are, we're always looking into integrating the latest and greatest sensors, and we definitely have. I don't know how much I can talk about, but we're testing new sensors regularly and often, and I guess stay tuned to our webinars, and we'll have new products coming soon. One thing, it's no surprise, we don't have a timeline or anything, but Regal has put out the VUX120 sensor, and so that can scan at different angles as a nadir scanner, and then 2 off naders, and so something like that is a new improvement. Other than that, the scanners that are available on the market right now and that we're integrating are the current latest and greatest, and I don't see anything absolutely revolutionary on the horizon, if that's what you're asking, to completely replace any of the scanners that we offer currently.
Okay, and I do have one more question for you, Corey, and this one is something that I hear from, that we hear about a lot. So from a post-processing point of view, what are your takes on multi-laser with 2 returns versus single laser with multiples, like 5 or 7 returns? I know this could be opening up a huge can of worms. It's going to be its whole separate webinar discussion. But a quick take. What's your feeling on that from the post-processing point of view?
I mean, from a post-processing point of view, if I'm going to be honest, then I would, choose the single laser with more returns than a multi-laser without. But there's a huge cost difference. So it depends on your budget and what you're trying to accomplish. So there's different applications for each sensor, and depending on your budget and your application, they're both quality solutions. But if I were to choose between the two, I'd certainly choose, say, a Ranger LR solution that can get 5 returns or 5 echoes and have higher accuracy and precision if I were to choose between the two.
Okay, fair enough. Thanks for answering that question. All right, I think that covers everything. Is there anything else you want to discuss, Corey, or do we think we covered pretty much all of it?
I can't think of anything. Yeah, I think that basically covers it.
Okay. All right, then. Well, thank you very much for your presentation, and thank you to the attendees for joining our February 2021 webinar on multi-vehicle, on different mounting for different vehicle setups, and look forward to seeing a replay of this session available on our phoenixlidar.com website in the next couple of days. If you have any questions, you can contact us at info@phoenixlidar.com. We look forward to seeing you at the next webinar. Take care, everyone.